After the introduction of the operation principle for data converters, now is the time to share the design for DAC, digital to analog converters. Yeah, anyway, you can see the same. For DAC, we have digital input from LSB to MSB, and then it will help us to create an analog output. That's it. Ideally, one LSB means the reference voltage divided by the 2 to nth power. Okay, right? That is the minimum and to the maximum. It dominates 50% of the reference voltage. Then allow me to show you what you already learned from microelectronics, but however, it can behave like in DAC. This is the summing amplifier. Look like this. Ideally, you can see, according to KCL, Kirchhoff current law, all the current flows in needs to reach the output through the feedback resistor, right? Because in theory, the input resistance of all those terminals, input terminals for op-amp actually is infinite, right? So how much current it will flow? Very easy. You can see, because this is, yeah, the voltage here and there should be equivalent in theory, according to virtual grounded for this terminal. Yeah, I think you already know the result. So you can see how much current here. Actually, it is V1 divided by R, right? And then V2 divided 2R, 4R, and 8R. All those current will flow through 8R to the output. So according to superposition principle, 重叠原理, you can see if I'm 1 and all the others are zeros. So you can see here to there will be multiplied by 8 times, right? And how about the others? The same. However, for V2 divided by 2R, then yeah, multiplied by 8R, so you got 4 and then 2 and then 1. Okay, bingo. This is what we want for DAC, right? And V1 is MSB, V4 is LSB. That's it. So in idea, this is such kind of very simple circuit can beat the so-called DAC. However, it is too simple, right? Then it has a lot of defects. Anyway, anyhow, allow me to show you some of them. And never mind, it is simple or not. All the circuits has their own defects. So from the very beginning, if something wrong with the resistors, for example, after fabrication, nothing is perfect, including the resistance, right? So if you can see for this one, I assume that all the others are perfect except for this one, okay? If after fabrication, R becomes a little bit larger, just like this, okay? What will be the result? So you can do it again, right? 1 here and all the other zeros, so divided by this and multiplied by that, so you get 6 instead of 8. What will go wrong? Monotonicity, right? You can see from the very beginning, all the bits are 0, so you get 0, right? And 0, 0, 0, 1, you get 1 all the way, right? Until what? Until 0, 1, 1, 1. You will get 7. After that, 1, 0, 0, 0, you get 6 instead of 8, right? So here, you will see monotonicity will be violated. Hey, pay attention to this. You have only 4 bits. LSB actually is your reference voltage divided by 16. If you get more bits, it means this one will be increased exponentially, right? So it means LCB will become very, very small, and I promise you, monotonicity is some kind of mission impossible for you to get. Okay, that is one of the issues. So what lesson you learned here? The more bits, the even harder to achieve monotonicity. 位元数越多哈，你单调性越难维持哈，因为你的那个每一阶的大小越来越小，随便一个风吹草动就挂了。However, don't tell me this is the only resistor will go wrong after fabrication. No, everybody. So after that, wow, it is not A, not 4, not 2, not 1, okay? So what is the result? Let's wait and see. Okay, again, the more bits, the more errors, the more inaccuracy you need to face after fabrication. Not only the resistors will go wrong, even the op-amp itself will also. For what? For example, the most important defect I mentioned is the input offset voltage. All right. So what is that? Again, according to superposition principle. All right. So you can have you ground over then and VOS here. So after some very brief calculation, you will get this. Okay. Just do it by yourself. So the input offset voltage of the op-amp will be amplified by such kind of non-inverting amplifier structure to reach the output. Right? All those terms, never mind your real input or some not so good input, will all be summed up to the output. So it means what? This will become the offset of the DAC. Because even you ground all the input, you still get this for output. So definitely, this is some kind of offset error for the DAC. And then, if everybody are correct, except for this, so what will go wrong? The gain. All right? The larger feedback resistor, it means the higher gain out of your expectation, right? Because if I got 10, sorry for that, you don't have 8, 4, 2, 1, the beautiful minorly weighted structure. Got it? Not limited to all the errors I mentioned. No, much more than that. So even this is a very, very simple structure. You still need to face a lot of errors. That is our life. Our life is much harder than digital IC designers. However, again, it will secure your own future because all the IC design companies need your help. They cannot do it, make it by themselves. No, all the dirty jobs, they need a lot of analog IC designers for help. Okay. So that is only a very brief introduction. Actually, for our real DAC design, we have 3 standard structures. Yeah, that is only for fun. Okay, only for fun. Oh, it belongs to current steering because all the currents needs to be turned on or off. All right? But from the beginning, allow me to show you, we have 3 kinds. First of all, voltage division. That is very simple to learn, but quite hard to achieve during many of the resistors you need to apply. Okay, but anyway, yeah, this is power consuming, because from the top to the bottom, it always consumes static power. You have no way to cut it down, right? And then the second, we call it charge sharing or charge redistribution. According to charge, 电荷, you need the help of capacitor. Right? Here, voltage division, you need R. Charge sharing, you need C. Okay? And finally, current steering, you need I, current. So resistor, capacitor, or current sources. That is three kinds. This is power wasting. That is, yeah, it doesn't consume any kind of static power, but with low operation speed. And for this one, it can provide the highest operation speed, but it will consume the most power. That is the major three structures for DAC design. Again, nothing is free. Here, power, there, speed, and this even more power for higher speed. If you would like to design the most speed, the fastest DAC, then you need to focus on this. If you would like to save the most power, you need to focus on that. So it means what? Usually we forget about that. Okay, that's it. Something in between, right? Not so good, not so bad, so nobody would like to use it. Anyway, it's only kidding. I would only like to tell you for power 7, this one. For operation speed, that one. Okay, keep this in mind. However, voltage division is some kind of DAC structure by nature. Yeah, if you have any kind of double E background, I think you will know what it would like to tell you, right? That's it. Okay, from the top to the bottom, we use resistors to divide the reference voltage, and then your input is used to select the proper one to be connected to the output. Piece of cake. Everybody knows it. Very simple. But yeah, it is quite simple. However, you still need to know some kind of operation principle and then try to do implementation. To know the operation principle and to implement it, actually, there are two kind of issues. Okay? It's really easy to understand. However, I'm not talking about the implementation is really hard. No, but you need another background for implementation. For example, the easiest one should be look like this. You have a lot of switches. And what is switch? In analog IC design, usually we have transmission gate. I told you already, one PMOS and the other one MMOS connected in parallel. Okay, and the control signals are complementary. If I'm 1, you are 0. If you are 1, I'm 0. That's it. To turn both transistors on or off. Okay, that's it. Anyway, what is operation principle for such kind of structure? Also very easy to understand. You can see from MSB, right? MSB dominate 50% of the reference voltage. If it is 1, what does it mean? Your output should belong to the upper half, right? That's it. If it is 0, it means what? Your output belongs to lower half. Okay, so according to upper half, lower half, we have 2 switches, right? If it is 1, it will go in this way, right? If it is 0, it will go in that way. Bingo! That's it. Right? 1, upper half, 上半部. 0, lower half, 下半部. Oh, beautiful. Okay? And how about the second bit to MSB? The same. If it is 1, because right now we are in the upper half, right? And then you will say, hey, if the second bit, second MSB is high, oh, congratulations, it belongs to the highest quarter. And then second to the highest quarter. Okay, yeah, that's it. Exactly the same operation principle can be applied not only to MSB, but to the second bit, the third bit, all the way to LSB. That's it. And finally, we will go, this way, that way to touch the proper voltage dividing node. That's it. Okay? Yeah, very simple, very easy. So it is not only simple to understand, it's not only easy to understand, but also to implement. However, nothing is perfect. It has some kind of defects. For example, for each node, it needs to pass through so many switches to reach the output before buffer. Okay? So it will cause a lot of delay if the number of bits is too high. That's it. Okay? Yeah. So if you would like to reduce the delay, it means for such kind of structure, it not only wastes a lot of switches, but also delay. If you have n bits, then you need to pass through n switches to reach the output buffer, right? So how can you improve such kind of structure? Before that, the other issue is you can see the breakpoints for the DAC. Yeah, you can see 0, 1, 2, 3 all the way according to LSB, right? And according to the definition of our INL, this one is no good because the error will become between 0 to 1 LSB. Okay, or -1 to 0. As you like, I don't care. Yeah. Anyway, the maximum error for such kind of DAC is 1 LSB. If you would like to reduce it to become 50% of LSB, then you need this structure in the middle. That's it. Piece of cake. All right? That's it. So you can see the bottom is not 1. That is not 0, sorry. 0.5, 1.5, 2.5, all the way. Got it? Allow me to point out something even more important according to such kind of balanced output, right? Don't be silly. You need to be smart instead of silly, okay? How to implement this? You say, I have one resistor. You need resistor for all the R's, right? All the R's are the same. And how about R/2? I cut it into halves. One for this, the other one for that. So that is piece of cake, some kind of piece of cake, right? However, it is no good. Yeah. If you would like to make it, I hope you don't do such kind of silly things, right? If you would like to match all of them, because everybody is important to provide the best voltage division, I mean close to optimum, close to perfect, then you need to apply unit resistors for everybody. Keep this in mind. Not only for us, but also for R/2. So what you can do? Don't divide it. No. And what else you can do? Anybody? How to achieve R/2 by the same unit resistor? Piece of cake. Yeah. 2 in parallel, right? That's it. Don't cut it into halves. that is some kind of silly implementation. Okay, all those to be matched should be exactly the same. So the most fundamental idea for matching layout is to apply unit devices. Everybody needs to be composed of exactly the same devices, sub-devices. Okay, that's your first step. But for real implementation, you can say, oh, 2 here, 1, 1, 1, 1, 2. No, it's still no good. Why? Because you need to have at least common centroid layout, right? With common centroid layout, you can get the best result. Otherwise, all those nodes won't get correct voltages after division. All right? So it is the other very hard issue for you to achieve. Okay, that's it. If you are interested, you can go back to study my analog IC layout classes online. Okay, just read it, just watch it by yourself. Here. Okay, that is the idea. Anyway, anyhow, even we change the, we call it R string. R string, right? A string of resistors. That's it. That is the simplest idea for such kind of voltage division structure. Even we change the structure of R string to make it balanced, to make the DAC error, from 1 to 1/2, bingo. But we still need to face the long delay caused by the switches. So the next step is to replace the switches structure from many layers, from n layers to only 1 layer. Okay, but how to make it? Through the help of decoder. All right, for example, 3 then to 8, right? Because input 3-bit, output 2 to 3rd order equals 8. So for such kind of decoder, actually from the beginning, it is applied to RAM SS, DRAM, SRAM, any kind of RAM, to select the proper cell, the memory cell to be accessed. Okay. Anyway, if you all those are 0, so this one will be 1. All the others will be 0. It means the lowest switch will be turned on. All the others will be off. All right, that's it. It means that 3 to 8, right? Never mind what is the input. Only one of the 8 switches will be turned on. All the others will be off. So you can guess this the minimum 0 here, 1, 2, 3, all the way. Oh, bingo, that is very good. Only one of the switches will be turned on to select the proper node voltage to be connected to the output, right? So it means from the R string to the output buffer, we only need to pass through 1 switch instead of n switches, right? It can help you to speed up the operation. Very good. However, nothing is perfect. You need to pay some price. For example, decoder is the major price you need to pay, right? Because if you go back to the original structure, you don't need any decoder. You just apply your MSB here all the way to LSB directly. You don't need any other's help. The input base can make it by yourself, in theory, okay, in theory. And how about in practice? Sorry for that, especially for LSB. Wow, it needs to turn on or off so many switches, right? It doesn't make any sense. The input bit may not have the good enough driving capability to do all of this. So you still need buffers. Okay? And to make matters even worse, 更糟的是啥？ For all the inputs, LSB to MSB, to turn on, turn off, all those, right? In theory, you had better turn all those switches on and off at the same time. Exactly. Otherwise, some is on, the other is off, sooner or later, it will cause some of the glitch to the output. Okay? Yeah, spikes here, over there, anywhere. It is caused by the, how can I say, not synchronized switching, unsynchronized switching. Okay, how to synchronize all the switch operation? Okay, we need to balance the delay from the input to the on-off of the switches. So it means we need not only buffers to enhance the driving capability, but also to balance the delay from the real input to each node to make all the switching happening at the same time. Okay? So it is called what? Equalizer. 等化器. You need to equal all the delays, right? So we call it equalizer. Please keep this in mind. It is a very important idea, not only for DAC, maybe also for ADC. Okay, let's go ahead. Now, all those ideas are replaced by a single decoder. Yeah, it can help you to save, in theory, again in theory, the equalizer. Okay? Because everybody only needs to turn on or off one of the switches, 1 to 1. Okay, so it is much easier to balance such kind of delay. So in theory, you don't need any kind of equalizer. And also, you can save a lot of switches. Here, you can see how many switches you need. Again, that is the order. All right? And then back to this structure. Oh, congratulations. You only need n switches instead of 2 to n's power. That's too many. All right? Again, all those are good. However, the major disadvantage is you need such kind of decoder. Luckily enough, such kind of decoder, it is in digital domain. Because I told you already, yeah, tens of years ago, or maybe more than 1 century ago, humankind applied decoder, encoder for RAM SSN to access the RAM, DRAM, SRAM, any kind of RAM, flash. Okay, so this is a digital circuit. If you have no idea how to implement it, no worries. You just Google online decoder, then Verilog. Yeah, all those keywords can help you download all the codes you need. That's it. Maybe the only issue is to modify, because nobody knows how many bits you need, right? So you only need to modify the number of bits. That's it. All the code actually you get can be applied directly for what? Automatic circuit synthesization. Then API, automatic placement and routing. Wow, the life is so easy in digital domain. So if possible, I hope you can make it through the help of EDA tools, not by yourselves. Okay, because through EDA tools, all those automatic design will generate the least errors. If you make it by yourself, it not only wastes a lot of your time, but usually you will get the most errors. Okay, we're humankind, we are not God. EDA tools are so complicated and helpful. Yeah, most of the bugs actually were released. Okay, no. Were dealt with before it is pushed to the market. Yeah. Anyhow. in this way, we can get help from some of the digital circuit to reduce the heavy burden of our analog design. So since after it is called digitally assisted analog circuit, right? As I mentioned, it is assisted by some kind of digital circuit here. Okay, digitally assisted analog circuit. That's it. All right. And also you need to pay attention. The other drawback is here. You can see for the input node of the output buffer, you will see not only the input capacitance of the buffer itself, but also if you look back, wow, don't always look forward. You need to look backward to see what's behind you, right? So in front of you, the input capacitance, and behind you, we have a lot of switches connected in parallel. So you see all the parasitic capacitance of them, right? So for embed, you see, that's too much again. Not only this, but also the input parasitic capacitance. All of them will be summed up to compose a huge capacitance here. But how to drive such kind of huge capacitance by the R string? Wow, it is some kind of RC structure, right? You can see to reduce the power from here to there, you need to increase the resistance. However, by increasing the resistance, you will harm the charging or discharging speed of the parasitic capacitance. You cannot please everybody. Okay, you can only please R or C, but not both. Okay, 你不可能取悦所有人. Wow, that is some hard issue for you to make the decision. If you would like to reduce R, then you need to pay the price for much more power consumption. If you would like to reduce the power consumption, then you need to increase the resistance. Then it is really harmful for the charging discharging of the capacitance, right? You will slow down your operation. That's it. How to break such kind of bottleneck? Okay, let's go further. Use matrix type decoding. Yeah, but before that, I mentioned already we have RC structure for charging, right? So for the charging operation, we need to know the time constant. Time constant, right? 时间常数. What is time constant? Actually, it is RC. Right? C we already know. And what is R? R is variable because it is different for each node you accessed. Right here, over there. Actually, the equivalent, if you look back, the equivalent resistance is different. For example, here, it means this in parallel with all of them. Right? Actually, it's small because this is a small a resistor in parallel with the large transistor, so the smaller one dominates. You don't need to worry about the charging speed here. It can help. All right. So what is the maximum equivalent resistance? You will see for this one in the middle. All right. To the top, to the bottom. Oh gosh, they are the same. So briefly, you have briefly, never mind for balanced or unbalanced structure. You have 2 to n power by R, right? So in the middle, to the top, to the bottom, they are all the same divided by 2, right? Right? And those 2 equivalent resistors will be in parallel. So divided by another 2, that's it. That is the equivalent resistance for the worst case. All right. So we have, see, 2 to n minus 2 power. Got it? Why we minus 2? I explained already. Right? That's it. That's it. So that is the maximum for you to estimate the settling time. Anyway, anyhow, again, R and C actually are contradictory to each other. Okay. Yeah. Anyway, you need to balance the speed and the power. It is really hard to design to make the decision. So let's go further. We need to change our mind. We need innovative structure. Allow me to show you. That is the first we can do. And to my memory, it is invented by Samsung. Yeah, the worst company. I mean, according to Taiwanese view. Okay, yeah, even worse than Chinese company. Because again, Samsung had some project called Kill Taiwan. I think till now, it still would like to implement it. So you announce that to 2030, it will kill TSMC. By killing TSMC, it will kill all the IC industry in Taiwan. By killing IC industry in Taiwan, it means kill Taiwan. Yeah, that's it. China will take the final advantage after Samsung kills Taiwan. Oh, anyway, anyhow, that's really upset. Hopefully, it won't be true. So for you, never mind, local or international students, please join us for IC industry. You can make a lot of money and also help us defend not only China but also Samsung. Okay, yeah, only joke. What is matrix type? You can see all folded. Okay, you can see here the R string is really a string. It is hand from the top all the way down to the bottom, right? That's it, right? So let's change our mind. We don't hand down the resistor string all the way from the top to the bottom. Actually, we can fold it. 我们可以把它折一下. Oh, like sausage, right? If you go to the market, you can see sausage like this, but it is very hard to store the sausage. You don't have such kind of long string of sausage put into your refrigerator. It doesn't make any sense. So we can fold it up, right? Sausage 1, sausage 2, sausage 3. That is what we can learn from the yeah, some kind of meat seller. 去跟卖肉店的老板学一下. We can fold the sausage to bake it, and it will become easier to store into your refrigerator, blah, blah, blah. Okay, that is what we would like to do. To fold, 折叠. To fold your R string, again, from the top to the bottom in this way. It is folded. Got it? In this way, we can reduce the upper capacitance very much. But why? All right, allow me to explain. But I need to explain the operation principle first. All right? If you fold it in this way, then we need two kind of decoders. The first for MSB bits, and the second for LSB bits. So you can guess, again, never mind how many input bits, we only generate one on output. All the other outputs will be off. All right, so you can guess for MSB bits, it doesn't help us to select the correct node. No, it helps us to select the correct fold. Okay, that's it. Because right now, for example, totally we have 4 bits. So 2 bits for MSB, 2 bits for LSB. Yeah, for easy comprehension. If I show you 12 bits, oh, all of you will be confused. So to help you understand the operation principle, I would like to make it as easy as possible. 4 bits good enough for explanation. Yeah. So we have 2 bits for MSB. For what? To select the correct fault. So you can see, again, the voltage flow is divided from the top to the bottom. The lower means low voltage, the higher means higher voltage. That's it, okay? So you can see, if I label the faults, okay? 我把它编号啊，每一组的编号 then you can see, it belongs to 0, 0, right? The lowest. And then 0, 1, 1, 0, and then 1, 1. Yeah, in this way, it explained so clearly by itself. It means what? For MSB bits, if it is 0, 0, then this one needs to be selected. This row, we have 4 rows or 4 faults, okay? In this way, we have rows and columns. So MSB bits help us to select the correct row. For example, if your input bits look like this, MSB bits 0, 1, right? 0, 1 means not this, not that. It means this row. Okay, so you can see, right now it is 0, 1. So the output is 0, 1, 0, 0. 1 means all the switches here will be turned on simultaneously, right? So it means what? The voltage of this row will be connected to all the output columns, right? At the same time, simultaneously. 这个 row 所有的分压会全部被粘到，被送到输出的 column 上面。Okay, so after that, this can help to select the correct column for output. That's it. Bingo, bingo. Okay. Yeah, so again, what is the LSB value? 1, 0, right? So you can see 0, 0, 0, 1, 1, 0, 1, 1. It is 1, 0. So this one. Because we have 4 columns. So this column voltage will be connected because this will be on. Okay? All the others will be off. So it will be connected to the output buffer. That's it. That's it. Piece of cake. Right? So in this way, you can see if you have n bits, for example, if you have 8 bits, then 4 bits here, 4 bits there. So for this node, again, if it look forward, you will see the input resistance of the buffer, right? If you look back, oh, you will only see 4 bits for the switches. So only 16, right? If you go back to see the original one, sorry, you have 8 bits. So totally, it means what? The parasitic capacitance is reduced by how many? By how much? Oh, 16 times. The more input bits, the more you can save for the input capacitance. Bingo. So it means what? Ideally, the operation speed can be enhanced by this 16 times higher than before. Wow, that is a huge increase. Okay, through such kind of innovative structure. Not only this, but also what? The size of the decoder will also be reduced because in the past you need 8 to 260 and 56 output. Oh, that is too much. So the complexity of the decoder actually depends on this, right? And right now we divide it into halves. So you have 2 of them, right? So you sum them up. It means multiply this by 2. It means 1 more. That's it. So the complexity of your digital circuit is reduced from 2 to nth power to this one, 2 to n by 2 plus 1. Okay, so again, for 8 inputs, this is 2 to 8. That is 2 to 5. So totally, you save 8 times for digital circuit. Wow. You can speed it up. I mean, according to 8-bit case, you can speed it up for 16 times. However, it can reduce the digital circuit by 8 times. It is some kind of mission impossible, right? You reduce the cost. However, you increase the operation speed. Wow. Really fantastic. Bravo. Okay. That is what I hope you can make in the future. To create something new. But again, you don't need to be Einstein. No. Just like if you go to the market to buy 1 string of sausages to bring it back, you need to fold it up. Then you say, oh yes. I wouldn't like to have such kind of very long string, right? You can still fold it up just like your sausages. Bingo, that's it. You can create something new to make a lot of money. If you are the one to create this, you can apply, you can file the patents to protect your innovation. Actually, that is not your innovation. You go to the market, you will see how to wrap the sausages to bring the sausage back, right? But you can copy and paste the idea from the other field into IC design. You can still create something new because nobody thought about it in the past. Then you make it. You file the patent, and all the IC design houses need to pay you, including Intel, Qualcomm, right? MediaTek, all of them need to pay you because you not only reduce the cost, but also enhance the operation speed. It is something very similar to Mission Impossible in the past, right? But you don't need to be very smart. No. Simply copy and paste. The sausage seller, the idea how to bring the sausage back. Copy the same idea to IC design, then you can make it. Anyway, that is really fantastic. However, there are 2 major defects here. Okay? I forget to tell you, not only the input capacitance here is too huge, and also for such kind of upstream for voltage division, you need to match all those resistors. If anybody going wrong, for example, this one becomes too large or too small, all the voltage divided will be affected because all of them are connected in series, right? One of them gets some error. The error will propagate to all the other node. Got it? 任何一个电阻出问题，就会影响到所有人的分压，它会扩散出去。Got it? So you need to pay a lot of attention to match all the resistors. Again, for 8 bits, it is something like mission impossible because you need to match 256 resistors all the way. Too hard. Too hard. It is really a heavy burden, especially for layout. Okay, so how can you reduce the heavy burden? If we come back here, can we make the matrix layout much easier than before? No. No. Why? Yeah, again, I told you already, the R string is folded only. If you pull them straight forward, they are still a R string, right? Exactly the same if you pull it, hand it down. It is exactly the same with this structure. So nothing is improved for matching. All right? If you would like to release the heavy burden for resistor matching, what you can do? Okay, let's go further. Oh, that is one issue. Later, I will explain. The other issue is before the break. Think about it. Okay? Again, please pay attention to the way we fold it. It is from the top to the right, then to the left, then to the right, then to the left, then reach the bottom. Right? What's going wrong with such kind of serpentine structure, sneaky structure, 蛇状的架构? Right? What's going wrong? Anybody? What's going wrong? Again, I show you. For the top one, to the right, then to the left, then to the right, to the left. Right? What's going on? The divided voltages. For this one, from large to small. For the next one, small to large. And then large to small, small to large. So it means the even or odd rows have different voltage division. From the larger one to the smaller one, or from the smaller one to the larger one. Got it? So it means what? For example, for this one, actually the smallest one is here, 0, 0, 0, 1, 1, 0, 1, 1, right? And how about the next? Sorry for that. The smaller one is here, 0, 1, 1, 0, 1, 1. Okay. That is my problem for you to solve during the break. What you can do? You cannot always apply the same decoder, because for the same decoder, if you have from here to there, 0, 0, 0, 1. Oh, sorry for this one. No good. Right? Right? Okay. Instead, 0, 0, 0, 1. Oh, good for it, but bad for that. Even and odd needs to change the sequence of the output, the sequential order, the order of the output. Okay, so again, for even rows, you need this 0, 0 to 1, 1. For odd rows, you need to reverse it from 1, 1 to 0, 0. So that is my problem for you to solve during the break. Be smart. You don't need to be Einstein again, right? You only need to be some kind of regular engineers. However, you fully understand what you learned from your text, or even from myself. Then you can make it. I promise you. Piece of cake. Piece of cake. Very easy to make. However, you need to be innovative. I already hint the result for you, right? For even rows, this one, 0, 0 to 1, 1. For other rows, 1, 1 to 0, 0. How to make it is up to you, okay? We can have maybe a little longer break because you need to think, and later TA will discuss with you when to do the third homework. Yeah, right? So it's up to you.